Okay, so starting off with this this diagram over here, as I mentioned to you before, you're getting these lines that are forming here. When you get something really narrow, sometimes you get this form, and these lines here are actually lines of destructive interference. You get waves being formed. We're going to try and understand what's that all about. Where do they come from? How does it work? And for a single slit, we're going to develop a formula for it. We're not going to go in all that much detail with it. If I just bring up the notes, I should have the notes here somewhere. Here are the notes, and I'll just show you whereabout we're working on. If you want to take notes here, that's great. You can also, from the PowerPoint, just take pictures of this and just put it into your notes. Try and do these with the least amount of. I don't want you spending forever on them. Just if you need to copy and paste from the PowerPoints, that's absolutely fine. So we're going to be looking at this point over here. Sketch the variation with angle of diffraction, the relative intensity of light diffracted at a single slit. So this idea of intensity of light is how we measure the brightness of a light. Now, intensity, I think, like this light from the projector is measured in lumen, but you do get something called candela, which is based on the brightness of a candle. So that's also another unit. I think that's your SI unit for brightness. And we're going to develop this formula. We're actually going to extend this formula, and in doing this formula over here, I'm going to be calling on some approximations or assumptions which you may find quite difficult to accept. Anyway, see how you go with it. Okay, so going back to the PowerPoint, let's bring that back up again here. And I'm mainly using this just to use the diagrams. Now, what we saw there by using with the laser is that we saw this. Now, this is a measure of intensity. So we saw this bright spot. Alright, so we saw this bright spot over here in the middle. And then you had your bright and bright. It was actually red light that we were using. So we saw that sort of situation there. Alright, and this gives an idea of the intensity. So when you measure the brightness, you get this sort of graph with intensity here. This is the formula that this is the diagram that they are asking you to draw in the notes and as part of the curriculum. Now, I don't know if you just want to go and cut and paste this. For some of us, our diagrams are just as good, if not better than these, but others are not so great. So you can decide what you want to do, how you want to do this. But we have this situation here. If I can move on, if you can come back to that and just finish that up. Now, we're going to try and look at some of the maths and also just try and see where this does come from. So I just want to pull up this diagram down over here. This one here. Okay, so this is our idea here that we've got our light coming in here. Now we used laser light, so we used what we call it's coherent. All the waves are coming in phase. So you've got one frequency of light coming in. So with a neon laser, it's the light is all coming in. We see it as red. Now, what happened was that we got this sort of pattern form where this was our real bright spot. We call this our principal maximum. All right, this is our maximum brightness over here. So this is what we'll call the principal maximum spot, and then we get our spot where it is dark here, and this would be our over here where we get our first destructive interference taking place. So at this point over here, somehow the light is converging or coming together in such a way that it cancels each other out. Now we're going to try and explain why that happens at a certain point, or what happens when you get destructive interference taking place. And so we're specifically looking at that situation. We're looking at where we're getting destructive interference. So obviously the combination of all of the light coming through is combining in such a way that it's all cancelling each other out. Now to do this, we use the idea of Huygens Principle, that if you've got a wave front coming through here, then each point on the wave, on that wave front, is a source of a new wave. So these are all sources of new waves. So we look at this, if we look at the situation here, we have it that if we take pairs, now we know that at this point, basically what's happening is that waves are coming in generally overall out of phase. That there is a half wavelength difference. A half wavelength difference between the waves that leads to a cancelling out. So overall, all these little wave fronts that are all forming are all leading to a half wavelength difference. Now, if I take this point over here and this point over here, if we accept that, then we would say that this point and this point, they are a half wavelength difference. So that would be your, I'll use different colors. So that point, and then this point over here, a half wavelength difference. So there is that length there is a half wavelength difference. If I took over the whole thing, we've got a full wavelength difference. But because we're looking at points along the way, pairs of waves along the way that cancel each other out, we take it halfway. We're actually getting a half wavelength difference over here. So if I take this distance from here to here, alright, and I call that x, let's call that x1. And if I take this over here, that distance, and I call that x2, what I'm saying is that on average, that always works out that x1 or x2 minus x1 is equal to a half wavelength. Alright? And if we are dealing, therefore, across the whole thing, we'll take that the difference between this point and this point over here would be a full wavelength difference. So this over here would be a full wavelength difference. Alright, does that make sort of sense? Am I making some sort of sense here?
When the x3 starts from the right angle, the y, or what's that called?
This lambda over here?
Yeah, how come the x2 starts like from the x, from the straight line?
Oh, sorry, this should start right from there, yeah. Yeah, that should start right the way through. Sorry. Okay, now we basically look at it like, I'll try and explain it again. I always find this, and perhaps if you could look for I'll look for some YouTube for somebody else to try and explain this better. But basically we've got this point and that point, say A1, A2, alright? They must be, because it's a minimum there must be a half wavelength difference. So then if we take this one over here, A3, A4, again, that same distance there leading to a half wavelength difference. A5, A6, alright? Again, a half wavelength. Overall, we're getting a situation that all the waves together are leading to a half wavelength difference. So we take, on average, therefore, for the whole thing, on average, the middle one, there would be a half wavelength difference. And therefore, the full thing, at the extremity, it would be a full wavelength difference. Okay? On average, in the middle, we have got a half wavelength. If I just by similar triangles, if this is exactly halfway in between here, So if this equals that, then if this is half a wavelength, then that must be a full wavelength. Now the formula that we have to develop is very straightforward because it just looks at this triangle over here. Okay, and from this triangle, if I draw this triangle over here, if that's theta 1 over there, this is b and that's y, then we know from the sine of theta 1 would equal lambda over b. Okay? Okay. Now, we use an approximation here that the sine of theta is equal to theta when theta is small and theta is measured in radians. Have you seen that approximation before? I would like you just to try that. I would like you to find the sine of 1 degree in radians. Okay? Find the sine of 1 degree. So what we'll do is we'll divide that by 360 and multiply that by 2 pi. Alright? And find 1 over 360 times by 2 pi. And see what the difference is. Okay, when you find that, Tom is just doing that for us quickly. What do you get for? It's pretty much the same, hey? It works out when the angle's small, this holds true. That you can say that the sine of theta is equal to theta. So in this formula, therefore, I can therefore just say that theta is equal to lambda over b. Alright, I can approximate that theta is equal to lambda over b, where this theta is the amount that we're looking at the wave is actually deviating. That's actually deviating, yeah.
So what is the B?
The b is the width of the slit of that the light is actually going through. The lambda is the wavelength of the light, and this theta is the amount that the angle that it's moved through. Okay.